Hi guys, my name is Mark. Today we're going to be looking at the higher level 2022 chemistry paper, specifically question 10, which is a multi-choice question. So in this case, let's get straight into part A. So moving into part A here, and kind of the way that the question 10 works is there's going to be three parts A, B, and C in this case, and you have to do two of them. And they all tend to be kind of grouped around different kind of sections in the chemistry course. So part A in this instance is going to be talking about kind of gases and the ideal gas law and all of these kind of terms like that. Part B will be something different and C will be something different again. And you only have to do two of them, but in this case we're just going to have a look at all three of them. So having a look at part A specifically, we're going to be looking at part I to start with. And in this case we're asked for a simple definition, which is what is meant by the term ideal gas. So in this case, unfortunately, this is just a straightforward definition, so you either know it or you don't. But in this case, an ideal gas is one that obeys the formula PV equals nRT. And this is done under all conditions of temperature and pressure. So it's important to note that because it's kind of an intrinsic part of the definition. So in this case, you could say that there's a few different ways you could phrase that. But this formula here, just to put a little star beside this little formula here, sums up several of the gas laws. And if you wanted to say them all separately, for example, an ideal gas law, or an ideal gas, should I say, is one that obeys Boyle's law, Charles' law, so on. That's perfectly fine, but you need to mention that it has to be for all temperatures or all conditions of temperature and pressure, because it's quite important. But either way, these are the important things that you need to include, mainly PV equals nRT in this case. So the total amount of marks going for this question was a nice handy 4, and those 4 marks in this instance were going for dropping the PV equals nRT formula, or saying, you know, it follows all of the gas laws. And yeah, nice easy 4 marks if you're able to recall your definition. Moving on now to part 2 of the kind of section A on the gases and gas laws. In this case, we're asked to state the conditions under which real gases come, closest to being ideal. So there's going to be several parameters that we need to include these conditions, and we want to have them such that these real gases they come the closest they actually can to becoming what we call an ideal gas. In this case, the conditions that we need to include to get full marks are that the real gases are close to being ideal when subject to higher temperatures, that's the first one, and lower pressures. So these are the important things. The real buzz terms to take away from this are high temperatures and lower pressures. And when we, subject a real gas to these conditions, either one of them, what you'll see is that their behavior actually becomes very close to that being an ideal gas, which is kind of what we're being asked for in this question. So yeah, those are your 2 buzz terms. There was a total of 6 marks going for this question, and the breakdown was fairly simple. You got 3 marks for saying higher temperatures, you got a further 3 marks for saying lower pressures, and yeah, that gives you your total of 6 marks. So moving now on to part 3, we were asked which of the noble gases would you expect to behave most like an ideal gas. So we're looking here at the noble gases, and then we're asked to justify our answers. So there's 2 important things that we need to take away from this question. We're being asked which noble gas, should I say, is the most like an ideal gas, and we're also being asked to justify our answer. So we need to include both of those in our answer here. Now, if you don't give the correct noble gas, then you mightn't, then you won't be able to get the marks for justifying it. But if you got the noble gas and you made a mistake with the justification, should I say, you will get some marks. So either way, it's important that you don't forget or leave out one of them. So let's have a look at our answer. And the first thing we had to do was identify which of the noble gases that we believe was the most like an ideal gas. In this case, the answer should be helium, or you can also write this as its like symbol on the periodic table, which would be He. And our justification, which is also equally as important, and in this case, our justification is that helium atoms have the least electrons. And subsequently, should I say, the element has a lower boiling point and weaker intermolecular forces. And this allows the gas itself to approximate more closely than any of the other noble gases that of an ideal gas. Now, there were several different ways you could approach this with different answers in terms of the justification. You could have gone down the route of saying that the atoms themselves are more like point masses, or they have smaller volume. I personally went down the route of saying they have the weakest intermolecular forces, and as a result, they have a lower boiling point. These are all acceptable answers. But either way, it's important that you remember to include the answer, helium, and also this justification. So there's a total of 6 marks going for this question, and the breakdown was as follows. You got 3 marks for correctly getting the answer, which in this case was helium, and then your justification got 3 marks. Now, in this case, I've actually included a little bit more information than you needed to. In this case, I included the fact that they have the least electrons, the fact that they have a lower boiling point, and weak intermolecular forces than some of the other ones. But even if you just said any of those singular terms, saying, maybe if you said, well, helium has the least electrons, helium has a lower boiling point, helium has a weaker intermolecular force, or should I say weaker intermolecular forces relative to other noble gases, you'll still get your full marks. But in this case, I was just covering all of our bases. So moving on to part 4 here, we're going to be asked a question that's going to be a little bit more tricky than some of the last ones, depending on how much you like the gas part of the chemistry course. And in this case, it's going to be revolving around a lot of maths and calculations. What we're told here is that the volume occupied by 4.85 grams of a gaseous compound was 60 liters. And this was, at a pressure of 99 kilopascals and a temperature of 22 degrees. So right out the gate, we're being thrown with a lot of information is being thrown at us. We're being told some mass, some volume, a pressure, a temperature. It's a lot, And what we're actually being asked to do is to calculate, correct to the nearest whole number, so that's an important thing to note at the end. You want to be rounding at the end, the relative molecular mass of the gas. So in this case, we're actually looking for our relative molecular mass. That's what we're actually trying to find at the very end of this. And you might be a little bit stuck with how to kind of start with this, but there's always a go-to formula when it comes to the gas laws, and it is PV equals N or T. Now I'm going to show you where that is in the log tables, just in case you forget it on the day, but this formula is super important, and I highly recommend that you get super comfortable using it before you go into the exam. So if you're stuck for the formula for these gas laws, PV equals N or T, if you just can't remember that off the top of your head, or you want to make sure that you're not making a mistake when writing it out, where you need to go in the log tables is to page 64 in the chemistry section. So in this case, if we look for the universal gas equation, what you'll find is this formula here on the left, should I say. So PV equals N or T. And there's a little bit extra added on there, but we're not too worried about that. We're just worried about this little bit here, which is PV equals N or T. So I'm going to go back to our question now, and then we're going to use this formula to hopefully get our answer. So writing down my formula here, PV equals N or T, we can actually go ahead and start plugging in all the information that we know. So what do we already know? Well, we know the pressure, which in this case was 99 kilopascals. So 99, and this is going to have kilopascals, so we're going to have by 10 to the 3. You can also write this out as just 99,000 if that's a little bit more comfortable for you. We're then going to have our volume. Our volume here of 60 liters, so we need to convert this into meters cubed, I believe. So 6 liters in terms of meters cubed is going to be 0.06 meters cubed, and then we need to let this equal to N. So N here is going to be the number of moles. Now we don't know what N is, so let me just write in N for now. Or which is going to be a constant in this case, it's going to be 8.31. Now, depending on the question, sometimes they'll actually give it to you. This is a constant that's actually also in your log table. So if you're ever stuck, I highly recommend that you go and pluck it from the log tables, just so you're not making a mistake. And then we need to multiply by our temperature in this case, which is going to be 22 degrees Celsius. But the problem is this temperature needs to be in Kelvin. So we're going to need to convert this to Kelvin first. So as I was saying earlier, we need to convert this 22 degrees Celsius into the Kelvin temperature equivalent. And the way that we're going to do that is by adding onto this 273.15. And the reason that we're doing that is because in order to go from Celsius to Kelvin, you need to add 273.15 onto whatever your Celsius figure is. So in this case, that's why we're adding it up. So now what I'm going to do is rearrange to find N. And the reason I'm rearranging to find N is because it's the unknown in this equation. So N in this case is going to equal to that 99 by 10 to the 3, which is our pressure, times our volume in meters cubed, which is 0.06. And then in order to get N on its own, we need to divide by our 8.31, our constant, and then as well as our temperature in Kelvin. So adding 22 degrees onto this, we're going to get 295.15. So pulling open my calculator here, I'm just going to fill in all of the information that we know. So on the top, we're going to have brackets 99 by 10 to the 3, which is 99,000 as well. We're going to have this multiplied by 0.06. And then on the bottom, we're going to have our constant, which is 8.31, and then multiplying this out by 295.15. And this will give us an answer of 2.42 moles in this instance, 2.42. So writing this out, we're going to have the number of moles to be 2.4, and I'm just going to round this up to be 2.42, and I'll just write moles. So we're going to be using this now in the next step in this question. So now that we know the associated number of moles here, we need to find our relative molecular mass. And the reason that I've pulled out our little our triangle here, our conversion triangle, is because we need to find an unknown, and what we are given already is a mass, and we're also given a number of moles, which we just found. So we're looking for a relative molecular mass. So relative molecular mass in this instance is going to equal to the mass that we were given divided by the number of moles that we have. And we were already told that mass, should I say, so the mass that we were given was 4.85 grams, and we want this mass to be in grams. And then on the bottom, we're going to have our number of moles. So our number of moles in this case was 2.42 moles. And I'm going to pull out my calculator and throw that into it and see what we get. So pulling open my calculator here, we're going to have a fraction, and on the top of this, we're going to have our 4.85 grams, our mass, and on the bottom half, we're going to have our number of moles, which in this case was 2.42. And the answer we're going to come out to with here is 2.004, and I'm just going to write that down, rounding it out to 2. So rounding that out to 2, we actually get our answer here for the relative molecular mass. And remembering back to the start of the question, we're asked for this in the nearest whole number. So in this case, if you wrote down 2.0004, it's really important that you round that to 2, but in this case, I've already done that. So yeah, that's this question finished. There was a total of 9 marks going for this calculation because it was quite a large one. You're using a lot of different formulas from different places. You got your first 3 marks for correctly writing out our formula. So in this case, this formula here to find n is going to give us our first 3 marks. You get another 3 marks for getting the correct answer here for the number of moles. As long as you got 2.4, and whatever came after that, any more decimal places, that's not really as important as long as 2.4 was the first 2 numbers you had. And the reason for this is some people might include things to different decimal places, and that's completely fine. As long as you were getting 2.4 something, it was completely fine. And then finally, you got your last 3 marks for getting the answer at the end, in this case, which was 2. Now that we have finished part A, we're going to take a look at part B. And in this case, part B, the first question we need to answer here is this one, which is to define the term electronegativity. So much like kind of all definitions, unfortunately, there's just kind of a right one and a wrong one. And yeah, let's go have a look at the correct definition. So for this question, the kind of required definition is such that electronegativity is defined as the number expressing the relative attraction of an atom for a shared pair of electrons in a covalent bond. So a covalent bond is also an important thing to note there. There's a lot of buzzwords you need to include, but the main ones in this instance is the relative attraction of an atom. That's a really important one to include here. And as well as that, you need to say that it is for a shared pair of electrons in a covalent bond, should I say. So yeah, that's kind of all you need to include in order to get your full marks. In this case, there was a total of 6 marks going, and as I was saying, the breakdown was 3 marks for saying, you know, relative attraction of an atom, and then the other 3 marks was for mentioning the fact that it is for a shared pair of electrons. So now that we have finished part B, we're going to be moving into some of the subparts here as well, which is means we're going to be given a little information beforehand. In this case, we're asked to initially account for the decreasing trend in electronegativity values down group 17 of the periodic table. So that's the first thing we have to do. And then once we're finished that, we're asked to do some predictions. So in this case, we're asked to predict the shape of a molecule of silicon tetrachloride, or SiCl4, a colorless liquid. So first what we're going to do is account for that decreasing trend in electronegativity, and then we're going to have a look at the shape of the molecule. So we need to first account for this decreasing trend in electronegativity values as we go down group 17. And the way that we can account for this is as follows. The electronegativity decreases going down group 17 as the atomic radius and the screening effect increase going down the group. So they're both important things to note when we're talking about this overall decrease in electronegativity. The atomic radius is increasing, and the screening and kind of the shielding of the nucleus, it's also increasing as well. So kind of giving you a little more context about what that means, as electronegativity has to do with as we were saying earlier, the relative attraction for a shared pair of electrons in a covalent bond. Now, as we get further and further away from the nucleus, as a result of that increasing atomic radius, what's actually going to happen is there's going to be a larger gap there, and this results in an overall net decrease in the electronegativity. And moreover, as we get bigger and bigger atoms, so as we're going down that group 17, we're going to get bigger and bigger atoms, and it means there's going to be more and more electrons in those inner shells, and as a result of them all kind of being there, they're going to kind of push against each other, creating the shielding or screening effect. And because as we get bigger and bigger atoms, there's going to be more and more screening. This overall also contributes to the fact that there's a decrease in electronegativity going down that group 17. So moving on to the second thing that we have to do here, which is the prediction of the shape of the molecule. In this case, the molecule we have to predict the shape of is SiCl4. And I've just kind of drawn that out here on the right hand side, as we can see in this kind of lighter pink almost color. And what I've done here is I've drawn a central silicon atom with several chlorines, actually 4 chlorines should I say, all orbiting. So 1, 2, 3, and 4. And these chlorines are all going to have should I say single bonds with the silicon. So when we're kind of observing this molecule, what you'll notice is that there's no actual lone pairs. They're all the bonding pairs. There's 4 bonding pairs, should I say. And as a result of them all having, all being bonding pairs, and there's 4 of them, and there's no lone pairs, they all push against each other equally. And this means that they are all going to occupy kind of distances as far away as possible from each other as is kind of physically possible. And in this case, it forces them to take a specific shape. In the case of this molecule here, that shape is actually going to be a tetrahedral kind of arrangement. And it results in, this allows all of the bonding pairs to be as far apart from each other as possible. And this is kind of the state that it's going to go into, as we can see kind of in this drawing. And just if you were kind of a little bit confused, these little kind of dashed lines and this kind of strange almost kind of triangle here are just trying to represent the fact that this chlorine back here is actually being pushed almost back into the page, and this chlorine towards the front is actually coming towards us, because this is actually a tetrahedral arrangement. Is going to be a 3D shape, which is a little bit more difficult to draw on a page. So in this case, we're using these dashed and kind of almost triangular lines to show what's happening here. In this case, there was a total of 3 marks going, and those 3 marks were associated with getting the right answer here. So tetrahedral is 100%. Another thing you could have said was a tetrahedron, and a diagram also would have sufficed. So if you could draw on the diagram that we have here as well, that would be perfect. But it's important to kind of, it's important to show the fact that some of the bonds are actually going in and out of the page, because it kind of gives the idea that it is a 3D molecule, which it is in case. So moving on now to part 2, which is going to be the second part in the kind of prediction of the shapes of molecules. In this case, we're asked to predict the shape of the molecule sulfur dichloride, which is SCl2. And what we need to do here, personally, the way I find this just the easiest is to write down or draw out roughly what you think it's going to look like. And in this case, you might be able to identify what the central atom is going to be. And from there, we can actually make some, do a little bit of work to kind of help flesh out our answer. So just over here on the right hand side, I'm going to draw out kind of roughly what I think it's going to be. So we're going to have a sulfur in the middle, and we're going to have 2 chlorines bonded to it in this case. And that means that the sulfur is going to be the central atom. Now, having a closer look at sulfur in this case, sulfur is going to have an atomic number of 16, and it's also going to be in group 6. And what that means, it's going to have 6 valence electrons. So basically, that's important to note when we're looking at kind of the shapes of molecules, because the valence electrons are actually just super important. And in this case, what we have is 6 valence electrons for sulfur. Now, the 6 valence electrons, these, this is not a sufficient number. And the reason it's not sufficient is we want to reach, or sulfur, should I say, wants to reach a, it wants to satisfy the octet rule. And as a result of that, it's going to want to have 8 electrons in it. So in this case, it's going to bond, it's going to bond with these 2 chlorines that we have here on either side, to give us those remaining 2 electrons. And I'm just going to kind of draw out what's exactly happening here to give you a little bit of a better idea. So down here on the right, I've drawn out kind of a rough dot and cross diagram of our sulfur dichloride. And the reason I'm doing this is because it just helps me understand what's actually going on here. Our 2 chlorines in this case are both in group 7, which means they have 7 valence electrons, and that is what is represented here with all of these individual X's. What you'll notice is there's 7 X's around each of these chlorines. And it means that in order to satisfy the octet rule and reach a stable arrangement, they need to have another electron, because 7 plus 1 is going to equal to 8. And in this case, they can't get that on their own. As a result of this, they're going to actually bond here with the sulfur in the middle in this case, and it's going to, they're going to share one of the valence electrons in the sulfur. So for example, what we'll see is that these dots on either side of the sulfur are going to become part of these kind of shared covalent bonds between the chlorine and the sulfur. And what that means is that the chlorine is going to be now sharing, it's going to have its seven valence electrons already, and it'll be sharing another one with the sulfur, giving us a total of 8. So each of the chlorines are now in a happy, stable kind of arrangement. And similarly, the sulfur in the middle, which we were talking about earlier, has those 6 valence electrons, so it needs 2 more electrons to be happy. In this case, it's sharing 1 electron each with the 2 chlorines, which means it's going to also reach a stable arrangement. However, once we have kind of had a look at what's happening with the two, the 2 chlorines and the bonds that are happening there, those bonds that we were kind of identifying, what you'll notice that there's actually some extra electrons around the sulfur. These 2 up the top here and 2 down the bottom, and these are known as lone pairs. And hopefully you've kind of had a look at them already. And these lone pairs are actually super important to the kind of shape of molecules because they push on each other a lot more than they push, or should I say, bonding pairs push. So as a result, it means that they're going to kind of distort the shape of the molecule. These bonding pairs are going to actually be a lot weaker, as I was just saying, and the lone pairs will actually push these bonding pairs closer together. So instead of everything, trying to be as far away from each other as possible, these lone pairs are going to be a little bit stronger. And it results in, not this linear kind of shape that we had expected at the start, but we're actually going to see this kind of almost V-shaped or bent molecule, as it's known. And the reason for it is because, and I'll just draw them in here, we have these 2 lone pairs up here at the top, and these are going to push on each other and push on the chlorines, and it's going to bring them almost a little bit closer together than they were if they were laid out straight. And it means that this kind of assumption that we made at the start, this linear molecule, is actually not right. This one down the bottom, however, is a little bit more, it makes a little bit more sense because we're taking into account those lone pairs. And as a result, the correct answer for this question is actually going to be not just a linear molecule, but what is known as a bent or V-shaped molecule. So just writing that down explicitly, the correct answer to this question is a V-shaped, or you could also just write it down here, and you could also say a bent-shaped molecule, or I believe angular would also be a correct answer. Now, a diagram is also acceptable, as it was in the previous question, so if that's kind of the route you went down with, that's perfectly fine. But it's just super important to remember those lone pairs, because it's very easy to forget them. And in this case, making sure to get all of this correct would have gotten you a total of 3 marks. And in this case, you just need to include either of these answers, so V-shaped, bent, or I believe the other one I said was angular, would all get you those 3 marks. So moving on to part 3 here, we were asked to determine the overall shape of the molecule of phosphorus trichloride. And in this case, our central kind of atom is going to be that of a phosphorus atom. So what we need to do here is kind of understand phosphorus a little bit more in depth. So first thing we can note here is that phosphorus is actually going to be 15 in terms of atomic number, and it's also going to be in group 5. And what that basically means is there's going to be a total of 5 valence electrons, so 5, and then e to the minus 1 in this case, it just means electrons because they have a negative charge, so 5 valence electrons. And as a result of this, it means that it needs another 3 electrons to reach a stable arrangement. Now, another thing to note here is that we're going to have 3 chlorines kind of just floating around in this situation as well. We have those 3 chlorines, PCl3, and each of these are going to have a total of 7 valence electrons. And we know this because they're in the 7th group on the periodic table. It means that these each need 1 more electron individually to reach a stable arrangement. And what they're going to actually do is they're going to share one of those electrons with the phosphorus in the center. And as a result of this, it means that that phosphorus, which needs 3 more electrons to reach a stable arrangement, it's going to get those 3 electrons, 1 from each of those chlorines. And the chlorines are going to be more than happy to do this because they're getting to share 1 electron with the phosphorus, which they need to reach a stable arrangement themselves. However, as a result of this, what we're going to have is we're going to have 3 valence electrons being shared around, and each of these bonds means that there's going to be 1 electron being shared, or should I say 2 electrons being shared in each one of these bonds. There's going to be a total of 6 electrons, and it means that left over there's going to be actually 2 electrons associated with this phosphorus atom in the center, which are not actually included in this bonding process. Now, as I said previously, these are going to be known as the lone pair, or the LP in this case, and it's going to actually overall distort the shape of the molecule. So the drawing that we have at the minute was just kind of a rough sketch to understand what was going on, but now I'm going to draw a little bit more of a kind of clear and actual correct drawing to show exactly what this lone pair, how does it actually distort the molecule. So this over here on the left hand side is going to be a little bit more of a honest and realistic drawing of our PCl3, and the reason that it's going to be a little bit more kind of aligned with what it actually is because we've included this lone pair up the top, but we're showing that it's actually pushing all the chlorines down. So if there wasn't a lone pair, all of these chlorines would move to an equidistant standpoint where they're all as far away from each other as possible to be as stable as possible. But because the lone pair is present, this LP, as we were talking about earlier, pushes more on the bonding pairs than another bonding pair would push on another. As a result of this, it means that these bonding pairs that would normally be equidistant are actually being forced closer together, resulting in a distorted shape to the molecule. In this case, the name for this distorted shape is triangle pyramidal, but the important thing to take away is this pyramidal term. And you can kind of understand why it's called pyramidal. What you have is this phosphorus at the top, and then the three chlorines being kind of pushed down towards each other, creating this pyramid almost like shape. And in this case, in order to get the full marks that we're going, so there's 3 marks going, you needed to include this term pyramidal, but also the drawing would have worked as well. Moving now on to part 4, here we're asked which one of these 3 compounds is nonpolar. Now, let's just first of all recall the 3 compounds that we were working on earlier. The 3 compounds that we were working with earlier was silicon tetrachloride. That was the first one, which is SiCl4. The second one we were looking at was sulfur dichloride, which is SCl2. And then ultimately we were working with phosphorus trichloride, which is PCl3. Now, the real question before we can kind of get into this is, what does non-polar mean in this context? And, we're kind of looking at this from the perspective of kind of the shape of the molecule. So let's just ignore electronegativity values just for a moment, and let's look at what the non-polar, in this case, means with reference to the shape of the molecule. Well, non-polar is extremely, important, and kind of refers to the fact that, a molecule is non-polar when the net kind of center of charge is in the middle of the molecule, and it's nicely balanced. And if it's not nicely balanced as a result of, maybe there's some lone pairs present, or there's a bit of a strange shape going on, it means that the molecule itself is polar. So just to start out, I'm going to draw out all of these molecules and the shapes that we kind of found for them. So the first we're going to have is this silicon tetrachloride. So we're going to have the Cl going up here, another Cl here, a small little triangle coming down the front, that's going to be another Cl, and then our kind of dashed lines showing this 3-dimensional shape drawn onto a page. Then we had our sulfur dichloride, which is going to have our 2 lone pairs, and then we're going to have our Cl and our Cl, and then ultimately we're going to have our phosphorus trichloride, which is going to have that lone pair at the top, Cl going over here, a little triangle going over here, and then once again our kind of dashed lines showing that this is like a pyramidal. Then let's have a look at each of these individually and determine whether they're non-polar. Starting out with the sulfur dichloride, what you're going to note is that there's actually going to be a net negative charge being stored a little bit down from the center. And the reason because of this is because we have 2 lone pairs at the top pushing these chlorines down, and these chlorines are going to have a negative kind of effect on where the net charge is going to be, and it's going to drag it down from the center. And as a result of this, it means that this molecule actually isn't non-polar because it's not symmetrical in terms of where the charge is being stored. And what we can call this molecule, this is going to be a polar molecule. Similarly, for the phosphorus trichloride, I believe it's called, what you're going to notice is this lone pair up the top is going to once again force all these chlorines down a wee bit, and this is going to result in the net center charge not being in the center, which is required for that non-polar name for the molecule. So in this case, this will also be a polar molecule. This leaves us with our final molecule over here, which is of course going to be non-polar because one of them has to be non-polar. But if you want to understand why this is the case, we have a 3-dimensional shape here of a kind of like a tetrahedron, and each of these chlorines is going to balance each other perfectly, and it's going to mean that the net center charge is going to stay exactly in the center, and this symmetricality is going to result in a non-polar molecule. So ultimately, the correct answer in this case is going to be our silicon tetrachloride, and you get 2 marks for getting that correct. So in this case, our silicon tetrachloride was the non-polar molecule. So moving on now to part 5 here, and the last question being asked is, out of those 3 compounds, which of them has bonds that have the least degree of polarity? So that's what we have to do here, we have to determine which of them has the least degree of polarity. And the way we're going to be doing, or should I say, the way that we're going to accomplish this is by using the electronegativity values given to us in our log tables. So that's what we're going to do. We're going to just jump straight over to our log table. So having a look at page 81, we're going to see our electronegativity values given to us in the log tables here. So I'm just going to first jot down the molecules that we're interested in over here on the left hand side. So the first one we're looking at was silicon tetrachloride, so it's going to be SiCl4. The second one that we were looking at was sulfur dichloride, so SCl, SiCl2, so sulfur dichloride, and then finally we're going to have phosphorus trichloride, so PCl3. As well as this, I'm going to highlight these kind of inside of the periodic table themselves. So first we're going to be looking at silicon here, which is going to have electronegativity 1.9, and this is going to be working with chlorine over here. We're also going to have phosphorus over here, which is going to have be involved as well, and also sulfur. So these are, well, they're all grouped together nice and neatly in the periodic table. So inside each of these respective molecules, there's going to be, in the first one, there's just going to be bonds between silicon and chlorine. For the sulfur dichloride, there's going to be a bond between the sulfur and the chlorine, and there's also going to be, for the phosphorus chloride, there's going to be, or phosphorus trichloride, there's going to be a bond between the phosphorus and the chlorine also. So what we need to do now is determine the difference, which is going to be this Greek letter delta here, just the difference. And the difference in these electronegativity values is going to be very important in us determining which of them here is going to be the least kind of polarized bond. And the reason for this is because the least polarized bond in this case is going to have the smallest difference between the electronegativity values. So what I'm going to do here is find these differences, and all you have to do is just take away one number from the other, and you're going to get some number, and that's going to be your difference. So for the first one, what we'll do, and I'll just do it over here on the right hand side, for the silicon chloride, silicon to chlorine bond, I'm just going to do 3.16 from the chlorine minus 1.9 from the silicon, and that's going to be our difference. So the first difference here between the silicon and chlorine atom is going to be a difference of 1.26. The difference between the sulfur and the chlorine is going to be 0.6, and then finally the difference between the phosphorus and the chlorine is going to be 0.97. And the result, the one that we're looking for, the smallest one here, is going to be 0.6, which is relating to the sulfur chlorine bond that we did find over here in our sulfur dichloride. So coming back to our question at hand, it was which of these compounds has the bond that has the least degree of polarity. In this case, we found that the bond between the sulfur and the chlorine has the least polarity, and this can be found in the sulfur dichloride or the SCl. There was 2 marks going for this question, and you got those 2 marks for just kind of getting this answer here. And just the way that I tackled it there with the electronegativity values is the way that I would have done it in an exam. It personally makes the most sense because the difference in the electronegativity values is the important kind of observation, or kind of the important break that you need to make to get this question right. So now that we have finished both parts A and B, we're going to be moving on to section C of this question 10. So this is multiple choice, as we were saying earlier, and with these multiple choice questions, there tends to be a couple different topics, and almost always, should I say, they contain one that's going to be more related to maths, so it tends to be stoichiometry. In this case, we're going to be doing a little bit of that now. So in this question, we're asked a few questions involving stoichiometry and calculations, and what we're told is that it was found that 44.8 centimeters cubed of SO2 measured at STP, so standard temperature and pressure, and 2.4 by 10 to the 21 molecules of NO2 were obtained in the combustion of X. So in the sample of X that was burned, calculate the number of moles of, and then we're asked to calculate the number of moles of hydrogen. Now, before we go any further, there's going to be a little bit more information given to us in the kind of paragraph of part C. As always with question C, there tends to be, or not even question C, but these stoichiometry questions, there tends to be a lot more information given to you all at once. So let's go have a look at the question before we actually get straight into solve. So pulling up part C here, we're actually given a lot more information with this big paragraph talking about a molecule of a pharmaceutical X that contains these various elements in it. We're told a little bit of information about this, and when X is burned in XX oxygen, the only products are water, carbon dioxide, SO2, and NO2. And when a sample of X was completely burned, there was 0.018 moles of water formed. We were also told then about some carbon dioxide, which was produced in the combustion of X that was absorbed by potassium hydroxide, and it was found that 3.584 grams of potassium hydroxide reacted with this carbon dioxide according to this following equation. And then we are going to be getting back into that paragraph that we just kind of looked through already, which is talking about NO2 and the molecules, standard temperature and pressure and all. So moving back to what we're actually being asked here, we're asked in the sample of X that was burned, we're asked to calculate that number of moles of hydrogen. And there's a lot of information being thrown at us here, and it's important to actually break it down and figure out what's actually. So the first and really most important thing to note from part I here is that the number that we're going to be kind of using, the bit of information we're going to be using out of this big paragraph, is going to be the 0.018 moles of water. And the reason I'm going to be using that is going to be using it in kind of tandem with this relationship between water and the amount of hydrogens present in the water to find the number of moles of hydrogen in the sample of X that was burned to solve part I. So what do we know already? Well, we know that 0.018 mole of water was associated with this reaction involved with X. And we're going to be asked here to find the number of moles of hydrogen present in this substance X as well. And as we know, hydrogen is going to be, it's going to be H2 is kind of the base state that you're going to find it in, as hydrogen is a diatomic element. And if we know that there was 0.018 moles of water, well, what we can actually do is, by using the relationship with the fact that there's going to be kind of an equivalence here, if we take this 0.018 and multiply it by 2, because there's going to be 2 hydrogens here, and we're being asked for the amount of hydrogen, so H2O here for water, we know that there's going to be 0.018 moles of water, which means there's going to be 0.018 moles of H2. And what we're interested in is finding just hydrogen on its own. So I'm going to just multiply that by 2 to get hydrogen on its own. And that's going to give us an answer of 0.036 mole of just hydrogen on its own, which is what we're being asked about here. And in that case, that's kind of all you really need to do here. It's a little bit tricky because a lot of information is being thrown at us at once. But once you kind of boil it down to what really matters here, the answer that was required is that 0.036 moles of hydrogen, and for this there was a total of 3 marks going, and that 0.036 moles of hydrogen is what is required in order to get your full 3 marks for part I. So moving on to part 2 of kind of section C in question 10 here, we're going to be asked to find the number of moles of carbon in that compound X. And what we're going to be doing in order to find that is we're going to be doing something similar to what we did in the first question. We need to determine what information is important to this part of the question, and then use kind of the relationships between the number of carbons and kind of what else we might find throughout the question in order to find our final answer. So the first thing that we're going to do here is go back to our question. The important takeaway for in order to solve part 2 here, which is going to be looking at the number of moles of carbon, is actually going to be found in this area here. And the reason it's going to be found in this area here is because we're actually told that 3.584 grams of potassium hydroxide was reacted with the carbon dioxide according to this following equation. And that's really important because we already know now that we already know the mass of this kind of potassium hydroxide. We can actually use that to find the number of moles of the potassium hydroxide, and then use this to find the number of moles of carbon dioxide, and then that will give us in turn the answer that we need to find the number of moles of carbon on its own. So writing down the important information that we already know, what we're being told is that there is a mass of potassium, so it's going to be of KOH, which is going to equal to 3.584 grams. And what we're going to do here is we need to convert this into moles. Now, pulling up our kind of triangle here that's going to be used for mass to find mass, moles, relative molecular mass triangle, the one that we can use to kind of transfer between them. We're going to be using this here because we need to find the number of moles of KOH, and we're given the mass. So what we need to do here is we're looking for our number of moles, which means if we cover moles on our triangle, what we're left with is mass divided by relative molecular mass. So therefore our moles is going to equal to mass over relative molecular mass, and we already know the mass here is going to be 3.584 grams, and then on the bottom half we're going to have our relative molecular mass of KOH. Now I encourage you to look at your periodic table here to find that relative molecular mass. What you need to do is just add up the atomic masses of the constituent elements. So you're going to add potassium, oxygen and hydrogen together to get your total answer. So the relative molecular mass of KOH, well, what we're going to do is add up all of the bits kind of in it. So the relative molecular mass of just potassium on its own is going to be 39. We're then going to need to add our oxygen, which is 16, and then our hydrogen, which is 1. And if we throw this into a calculator, we're going to get our moles of KOH. In this instance, the number of moles of KOH is going to be 0.064 moles, and it means that we're one step closer to getting our final answer. Now, an important thing to note here is the actual equation that we were looking at for this question. What we were told is that 1 mole of the carbon dioxide, so it's going to be, so just to write this down kind of up here, 1 mole of the carbon dioxide is actually reacting with 2 moles of the KOH, and this is going to kind of carry out into, you know, whatever the rest of the reaction is. But we're really only interested in this carbon dioxide on the left-hand side here. Now, what we already know is the number of moles, and I'll just write this also up here. This is the number of moles of KOH. So we already know the number of moles in this KOH here, but we actually are told that, well, this is 2, you know, we have that relationship there for every 1 carbon dioxide, there's going to be 2 KOH. And what we need to do is we need to convert that to get the number of moles of carbon dioxide. So if there's going to be a 1-to-2 ratio of carbon dioxide to potassium hydroxide, what we need to do then is divide that 0.064 by 2 to get 0.032 moles, and in turn, by dividing by 2, we're actually converting from the number of moles of KOH to the number of moles of CO2. Finally, moving on from this last kind of little bit of information that we found, we have 0.032 moles, I'll just write it out fully now, of CO2, and what that's going to imply, this is largest, meaning that's going to, you know, what that's going to imply is that there's going to be 0.032 moles of just the carbon on its own. And that's actually what we're just being asked here for. We're just being asked, what's the number of moles of carbon here? And that's what we've kind of just found here in that last line. And there was a total of 8 marks going for this question because there was a little bit of calculation that needed to be done. And in order to get those 8 marks, well, you got those first 4 marks for correctly getting the number of moles of KOH. And then finally got another 4 marks for getting the answer at the end. And the process that I did here would be just kind of the simplest one that I would do, and even just drawing out the triangle here always is quite helpful, because sometimes it's very easy to forget the kind of arrangement of it and you might be kind of stuck thinking. But in this case, yeah, the answer that you needed to get your 4 marks at the end was 0.032, giving you a total of 8 marks. So for part 3 here, we're asked a similar question to the ones that we were asked before, but in this case, we're asked to find the number of moles of sulfur. So just like the previous 2 questions, I'm going to jump straight to the information that we're given in the question, and we're going to pick out what's important and what we need to use in order to get our required solution. So coming back to our question here, where is the first kind of instance that sulfur actually gets mentioned in a usable way? Now, you might be inclined to see up here where SO2 is mentioned, but in reality, that's actually not very useful to us because we're not told any information about the quantities, moles, or volumes associated with it. However, if we look at this last section here, we're actually told a lot of information about sulfur dioxide. What we're actually told is that it was found that 44.8 centimeters cubed of sulfur dioxide, so there's the sulfur that we're kind of interested in, measured at STP, and this 2.4 by 10 to 21 molecules of NO2 were obtained in the combustion of X. So that's a little bit of information that we can use to find the number of moles. The most important number actually here being this 44.8 centimeters cubed. So writing that down here, what we know is there's going to be 44.8 centimeters cubed of this sulfur dioxide. And that's all well and good, but you might be asking yourself, well, how am I actually going to convert this to moles, or how am I actually going to take this a step further? Well, what we do know is that this was measured at STP, or standard temperature and pressure. And what that basically means is we're able to use something known as the molar volume, and hopefully you've come across it before, to convert between the volume here of SO2 to the number of moles in the SO. So the way that we're going to do that is by dividing. So we're going to have that 44.8 centimeters cubed divided by the molar, and this is centimeters cubed, should I say, and dividing this by the molar volumes. So in this case, the molar volume is going to be 22,400 centimeters cubed. And I'll just write it up here as well. This is also known as 22.4 liters. So there's a couple of different ways you can do it, but we're just converting between liters and centimeters cubed in this case. So it's going to be 22,400 centimeters cubed. And by dividing here, what you know is the centimeter units will cross off, which is good. And what we're going to be left with, if you throw this into your calculator, is going to be 0.002 moles. And this is going to be of our SO2. So just written that down, SO2. And yeah, by using the molar volume here, we're actually able to convert and get the number of moles. Now, similarly to before, when we were looking at the carbon, when we found the number of moles of carbon dioxide, we actually already knew the number of moles of carbon. And in this case, it's exactly the same thing. So if we have 0.02 moles of SO2, just writing it down here, well, what this actually means is we also have 0.002 moles of just plain old sulfur. And in this case, that's actually just the answer that's required here in order to get your full marks. Now, there was 4 marks going for this question here, and those 4 marks were in fact going for this end answer here. It's actually very, very easy to get something like this wrong, because this 22.4 liters is kind of a little bit confusing, because sometimes, there's a different value for when it's measured at something that is at standard temperature and pressure. So when measured at standard temperature and pressure, it is that 22.4 liters like I have up the top here. But when it's actually measured at something like, for example, room temperature, it's a different volume. So just be 100% clear here that, which one's which. And in this case, 22.4 liters or 22,400 centimeters cubed relates to the molar volume at standard temperature and pressure. Once again, now moving on to part 4 here, we're going to be asked about the number of moles of nitrogen in this reaction. In this case, once again, we're going straight to our question to identify the key information that we need to solve this question. So once again, very similar to before, you might be very easily enticed into this NO2 that's mentioned at the top. But once again, we are not actually told any real important information about it. And there's actually nothing mentioned about nitrogen in terms of quantities, moles, or the kind of volume. But what we do know is that in this bottom section, similar to the sulfur dioxide that we did previously, there's actually a little bit of information given to us about NO2. And we're actually told that 2.4 by 10 to the 21 molecules of NO2 were obtained. And very similar to the previous process that we used to find the number of moles of the SO2, we can actually do the exact same process here and to find the number of moles of NO2, but instead of using molar volume, we're actually going to be using something a little bit different. So jotting down the information that we do know, we were told that there were 2.4 by 10 to the 21 molecules of NO2 collected. So just write this down, this is of NO2. And what we need to do is convert this into moles. Now, the way we can actually do this is by dividing by something known as Avogadro's number. Now, hopefully we've covered this. Hopefully you've covered this, should I say. But basically, by dividing by Avogadro's number, we're able to convert between the number of molecules or atoms or anything quite like that into a number of moles. So what we're going to do here is first divide by that number, and in this case that number is 6 by 10 to the 23. And when I do this, what we'll be doing is actually getting a number of moles associated with this NO2. So by dividing this into if you throw this into your calculator, what you're going to find is we're going to get an answer to be 0.004, and is going to be moles of NO2. And that NO2 is important because we're looking for nitrogen in this question. Very similar to how we did it before, and if we have that 0.004 moles of NO2, well, that also means that, so therefore the 3 dots here, it means that we're going to have 0.004 moles of just plain old N in this case. And that's exactly what we need for this question. So there's a total of 4 marks going for this question as well, and you got those 4 marks for getting this answer here. Yeah, like very similar to all the previous processes, all we have to do is identify the key information, do the correct calculation, whether it's divided by a molar volume, Avogadro's number, by finding the number of moles by using the relative molecular mass, moles, kind of triangle thing that we did earlier on. It doesn't really matter. This process is kind of similar for all of them. So just before we finish up question 10 part C here, and kind of question 10 in general, we've one final piece of the puzzle that we have to fill. And what it is that we're being told if there was 0.08 moles of oxygen in the sample that was burned, what is the empirical formula of X, listing the elements in alphabetical order? So it is a little bit of a mouthful, but basically what we're being asked to do is find that empirical formula of X and list the elements in just kind of the alphabetical order. So what we've already found in the kind of question we've already done is the number of moles in each of the constituent elements of this overall formula for X. And this is going to be super important because these moles, they're going to bear a resemblance to each other that's going to allow us to calculate the empirical formula. But what I'm going to do now is I'm going to grab all that information and write it down here in a simple and easy to understand way, and then we're going to use that to hopefully find our empirical formula. So what I have done is I've wrote down all of the elements that we have already worked with and all of the moles that we have found. So what we have on the left hand side is all of the elements that we've worked with, and I've rearranged them into an alphabetical order. So starting at C for carbon here and ending at S for, I believe it was sulfur. And what I've wrote down here is going to be the relative, or not even relative, but the ratios of these to each other. So on the right hand side, that's actually going to be displayed here. These are the ratio of the moles to each other. So for example, if you want to just take one element here. For example, we have our carbon here, and it's going to have the number of moles beside it, so 0.032, and the ratio of carbon to hydrogen is going to be 0.032 to this 0.036, and this is over here, this hydrogen, we've already found this, we did this at the start of the question. So all the information that we found previously is going to come in very handy here in terms of finding our relative, or should I say our empirical formula for X. So now we have all of the moles kind of arranged alphabetically and then put into this kind of ratio format, I guess. What we're going to be doing is, in order to find our empirical formula, we need to divide all of these by the simplest, or should I say the smallest number of moles. And in this case, the smallest number of moles here is going to be 0.002. And by dividing everything here by 0.002, it's going to convert all of these kind of partial, very small number of moles. It's going to convert this ratio into a whole number ratio. It's going to make life a lot easier to work with. So let's just kind of take that nice and handy. What we're going to have first is going to be carbon. And if we divide the first term here, so I'll just even circle it here, is 0.003 or 0.032 by 0.002. What you're going to come out with is carbon, and there's going to be 16 of them. And repeating the process for the next one, we're going to have hydrogen here, and dividing this 0.036 by our 0.002, you're going to come out with a total of 18. Moving on from that, you're going to divide 0.004 by our 0.002. This is referring to nitrogen, and you're going to be left with a total of 2 here. Moving on from that, we're going to divide our 0.008, which is going to be oxygen, and that's going to be divided by 0.002, and that's going to give us 4. And then ultimately we have sulfur, and if we divide our answer here at the end, 0.002 by 0.002, you're going to just get the left 1. And this is going to be our empirical formula. It's a little bit of a tricky kind of question to do, and hopefully you've kind of covered this in the stoichiometry section of the course, because this is kind of something that comes up, not all the time, but it is something that they like to ask sometimes. And in this case, there was a total of 6 marks going. You got 2 marks for correctly breaking down kind of this ratio of the elements into the alphabetical order, and then putting each of the moles that we found from previous questions into a ratio against each other. You got another 3 marks for dividing by the simplest, or should I say the smallest number of moles. So even just to draw that number 3 there, you're going to get that for dividing by the smallest number of moles to get those whole number ratios. And then ultimately you get your last mark here for getting it absolutely correct. So in this case, it's going to give you your total of 6 marks. Now this is quite a complicated empirical formula for X, and it's quite a, obviously you probably wouldn't know this molecule off the top of your head, but in this case we were able to find it by just rearranging it in terms of ratios and working from there.